Hi everyone, I am Siyu from MIT. Today I will be presenting an empowerment-based solution to robotic manipulation tasks with sparse rewards. The classical task and motion planning method to robotic manipulation often requires a significant amount of domain-specific prior knowledge, and many reinforcement learning approaches, on the other hand, typically only work well with well-structured environments and dense reward signals. However, if we hope to develop robotic agents that can be deployed in new environments and accomplish new tasks, it is important that the agents are able to effectively learn with minimum amount of human supervision. The intuitive way human users would prefer to define tasks typically only provide very sparse or binary rewards, which poses a significant challenge for reinforcement learning agents. In this paper, our goal is to minimize human supervision and the requirement on task-specific prior knowledge and allow robotic manipulators to learn tasks with sparse reward from scratch. We propose an empowerment-based intrinsic exploration approach that allows robots to learn manipulation skills with only sparse extrinsic rewards from the environment, and demonstrate its performance on an object manipulation tasks in two simulation environments, including OpenAI Gym and Gazebo. Core to our approach is the concept called empowerment. Empowerment represents the maximum mutual information between a sequence of actions and the final states conditioned on the initial states. In this paper, we assume that an accurate estimation of object poses can be obtained, and we divide the state space into intrinsic states and extrinsic states, where intrinsic states refer to the states of the robot itself, and extrinsic states are the states of environment objects. When computing empowerment, we then only use the extrinsic states as the next state in order to avoid the agent trivially maximizes the mutual dependence between actions and its own states. The intuition behind this modified definition of empowerment can be explained with an object manipulation example. When the robot is exploring the state space without any interaction with the object, robot actions and object states should be independent and the empowerment should be zero. If the robot is interacting with the object in a random manner, for example flipping it around the table or pushing it off the table, the state of the object is correlated with robot actions, but the correlation is difficult to predict, hence the empowerment value is low. If instead the robot is interacting with the object in a very principled way, for example pushing or lifting the object, the correlation between robot actions and object states should be much easier to predict, and the empowerment value should also be much higher. We evaluated our approach on object lifting tasks where the reward is given based on the height of the target object. Our empowerment-based learning agent is able to successfully lift up the object in every episode during test time, and it also achieved faster learning progress compared to other state-of-the-art intrinsic motivation approaches. When comparing the performance of our approach with the curiosity-driven approach in terms of learning a cylinder lifting task, we noticed that our approach is able to train the agent to directly lift up the cylinder, whereas the curiosity-driven approach makes the agent first knock down the cylinder before lifting it up. We also combine our empowerment-based intrinsic motivation agent with the diversity is all you need approach in order to learn a diverse set of skills. The videos show that with empowerment, the agent is able to learn different ways of interacting with the object, whereas without empowerment, the agent simply learns to move the manipulator in different directions without interactions with the object. To conclude, we propose empowerment-based intrinsic motivation, an approach that maximizes the mutual dependence between robot actions and environment states in order to help the agent focus more on the states where it can effectively control the environment instead of the parts where its actions cause random and unpredictable consequences. Through empirical evaluation in different robotic manipulation environments with different shapes of the target object, we demonstrate that this empowerment-based approach achieves faster learning progress compared to other state-of-the-art solutions to sparse reward RL tasks. Thanks for listening.